Okay, good afternoon, everyone. I'm Fabio Favoino. I'm a professor at Politecnico di Torino. I'm a building physicist as a background and worked a little bit in facade consultancy as a facade engineer, and then went back to academia. And I'm very glad to be here. I think it's quite like this setting of this conference. It brings together a lot industry, and so we wanted to present this small work that we did here, as I think it can give a little bit of contribution to the discussion related to how do we make a risk assessment for thermal shock in architectural glazing. And we were able to just have a small dive into this topic thanks to a research project that we won in a province of Bolzano in Italy that helped us in developing a little bit further a methodology. Well, we've seen that how the different ways a glass or a IGU or a laminated glass could break. There are other ways, not just impact winds, but also effect of sun and temperature difference can cause a fracture in glass. And why this is important? I would think that also in a decarbonization agenda of buildings, the fact that we are using more and more double and triple glazing units, more insulating with more glass layers, use of selective coatings for solar control and daylight. So effectively, we are quite absorbing a bit of solar energy. And that's also the fact that we're using frames that are more insulating. Effectively, we are increasing the temperature difference between the edge and the outer layer center of panel of the glass. So eventually, we could encounter more thermal shock risk in IGUs. And the way this is avoided usually is heat-treat the glass in conditions in which you could use heat-treated glass, depending on the kind of coatings, curvatures that you have. And eventually, this ends up in increased costs of heat-treated glass compared to annealed. The tempering process requires more energy, and eventually, this is a higher carbon footprint. So at the end, in a high GU, let's say that's more or less 15% of the embodied carbon A1 to A3 of an IGU can be attributed to glass thermal treatment. So there's also an environmental value there. What's the problem is that there are no internationally recognized standards to do a thermal shock risk assessment. There are some existing methodologies in national standards. French DTU 39P3 for IGUs and the ASTM only for laminated glass. These methods could be sometimes oversimplified. Means that maybe we are over-engineering the glass and the fact that we need to strengthen the glass. The question is whether these are accurate enough. So do they also give a good enough representation of the boundary condition that we have from the climate? And they are not probabilistic. Due to this lack of standard, of course, in the industry, there are a lot of best practices to solve this problem. And I mean, in this table, just a comparison between the two standard approach and let's more complex best practices related to how you choose the boundary condition, the kind of thermal model you use, and the structural model you're using. So the DTU approach, at the end, you use a static boundary condition only for French territory. The thermal model is a thermal model that is simplified, so one-dimensional thermal model for the center of panel and the edge, only in some condition for double glazing unit, and only partially for triple glazing units. The structural model is a deterministic model, so not probabilistic. Best practices that are used, and there are different works also published, work done by Permastilisa or University of Parma, in which there is a FEM structural model that is used to evaluate what is the thermal stresses related to temperature difference that are calculated though with a static boundary condition or dynamic, or sometimes like a coupled structural and thermal model altogether. So in any case, it seems that there is a little bit of a lack of a trade-off between, let's say, the accuracy or enough accuracy and the usability of thermal shock risk assessment for everyday use, because these best practices, of course, are very accurate, but maybe they're not. They cannot be used by, let's say, a normal engineering studio or a glass processor manufacturer. So they can be used for very special projects, condition, and so on. And also, vast majority of glazing at the ends are rectangular vision glass with framing, either window or curtain walls. So not very special condition. So thanks to this project, what we try to do is to develop a methodology that includes these four fundamental steps. So first of all, considering a probabilistic climate boundary condition. This probabilistic climate boundary condition gives a statistical representation of the climate, is then used to have a, let's say, accurate enough glazed, glaze and facade elements thermal models that spatially resolves this boundary condition for different tilts and orientation. And the temperature differences from this condition of the model are then used to evaluate the stress and compare it to the strength for a probabilistic glass model. And then finally, this is used to do a final thermal shock failure evaluation. So one by one, so within this presentation, briefly I'll go one by one of these different steps of the methodology. And then what we did is a validation with the inter-software comparison between this methodology and the NF, so the French standard methods. And then a kind of case study analysis to understand where this method could be valuable. So in terms of boundary condition, normally the DTU, what it does, it divides the nation or a certain geographical area in different conditions in terms of temperature or solar radiation, but these are accounted as, peak condition, worst case scenario. Instead, what we use is the available statistical representation of climates, which is called TMY, which is a 30-year representation of a climate in one location that then sums up in one statistical year. There are a lot of TMYs already for more than 60,000 climate locations in the world. That could be downscaled to a resolution of 5 kilometers by means of the PVG's software that can give not just solar radiation, but also temperature, wind speed, relative humidity of any location in the world with this resolution, but spatially resolved in any orientation and tilt, considering also the albedo of the context that is around. So then we elaborated basically two models. These are both resistance models, so one-dimensional lamp parameter thermal model that are, so there is one model for the center of the panel and actually different models for the edge of the frame. The center of the panel model consider the absorbed solar radiation in the different glass layers, of course, due to direct absorption and secondary interreflection between the different glass layer, and the surface transfer coefficients are divided between radiative and convective one, differently from the French standards, but then it doesn't consider the thermal capacity of the glass, so effectively every hour of evaluation is separated from the other. For the edge of the glass, we consider different models that account for different frame materials and especially the condition of the edge, whether that's exposed or not, and whether the frame is thermally broken or not, and whether it's window or curtain wall. So we develop different model about that. And then at the end, we consider the delta T, so the temperature difference that might induce thermal shock within one layer, as the worst combination between, let's say, the irradiated and non-irradiated center area of the panel and the irradiated and non-irradiated edge of the glass. This delta T is then used to calculate the thermal stress, and this is compared to the design strength of the glass, considering the EN 16612. In this case, what we use is a K mode of 1 hour due to the hourly resolution of the climate representation, but also due to the dynamics of transferring heat in the glass. That's in a, let's say, even in laminated glass are about hour. They have an hourly resolution. And then at the end, what we calculate is a utilization factor. That basically is just a ratio between the stress and the strength. That, of course, this needs to be below a certain level in which we are eventually removing a margin of error that we could assume based on the accuracy of our delta T. So how good we are in simulating the temperatures within the glass. This calculation is done for every glass pane of an IGU, and then we are eventually understanding, with this a carpet plot for a certain pane of the IGU, which we see the maximum, the temperature all over the year, but eventually the delta T and then the stresses. And this is basically the amount of time during a year my utilization factor is, let's say, below the, let's say, 1 minus the safety margin that we want to take, or eventually in a risky area, or if there is a red, it's a failure. So we'll not pass the, whether we are in yellow or red, we won't pass the thermal shock analysis. So what we did is first an inter-software validation and a comparison between our models related to basically window software, optics and window software, as far as the center of panel is concerned, for different IGU and optical properties. We validate the edge of the panel compared to BISCO thermal analysis in different conditions, so FM, 2D FEM analysis for different frames with exposure and capped edges. And then we also did the modeling for the NF, so the French national standard, to benchmark with our results. And for the national standard, we have two different models. We have a manual one and a simplified one, in which the manual one is the more simple. That is not dividing the transfer coefficient between radiative and convective. It's only valid for double glazing units. You don't have a model for triple glazing units. And edge conditions are only representative of non-thermally broken frames, while the simplified one, it's more similar to what we use, but is also simplified in terms of edge condition. So this is the results from the the comparison with Windows software, and the closer you are to the bisectrix, here you have the temperature of window, here you have the temperature of the different models. So if you are exactly on the bisectrix, of course, it's you're having the same results. And what you can see is that there is an underestimation of the temperature, especially in the triple glazing unit, when it comes to the NF models, while with our model are basically very close to the window results. That's for center of panel. When it comes to the edge, I'm just showing the results here for triple glazing units. That's where we don't have a model on the national standard, on the French standard. For thermally broken insulated frames and for a curtain wall with exposed edge. We did this analysis actually for 9 different frame configuration with also different edges configuration. What you see here in green are the results from the FEM analysis. In violet are basically the results from the French national standard of the edge temperature, while the yellow is actually the model that we elaborated that is based on FEM, but is a 1D model that is very, very close to the finite element thermal analysis results. So you can see that with the national standard, you have this 4 to 6 degree difference, and sometimes this is overestimating, sometimes this is underestimating, so it's not always in the same direction. While with our model, we are basically 1/3 of this difference, and again, this can be over and underestimating. So we tested this methodology for different configuration of glazing, from single to double and triple glazing unit with different optical properties. And you can see the different absorption of the different layers. And I mean, we did this only, what I'm presenting, only for aluminum thermally broken frame with a non-exposed edge for a south-oriented facade in Paris and in Torino, in Italy. Paris because it was in French territory, so we could compare like for like with the French standard. And also because it was important for us to understand the influence of how do I choose the boundary condition in my thermal shock risk assessment, in which basically we use 2 source of climatic data for our dynamic model. One is TMY with real sky, and one is a TMY with a model of only clear sky, which is the TMY plus Solis. Means that in that TMY, I'm considering that I have no clouds. I always have clear sky, while in the other one, I have the real one with the clouds. This is just a summary of the results for Paris and Torino for the different models. So the French manual simplified our dynamic model. So the DIN stands for dynamic model. And then the ASTM for single, double glazing and triple glazing units for different boundary conditions. So the standard is the national standard, French national standard within French territory, and then the TMY of just clear sky and the real TMY for the two locations. So what you see here is just a pass of fail for the IGU. So it's simply saying whether we could have thermal shock in that IGU or not, but actually behind this we calculate all the delta T for each glass layer. So this is one result, but then we went deeper to understand what was happening. And of course, what you could see is that for non-critical conditions, non-critical condition means that glazing that we knew that were not passing thermal shock or that would pass the thermal shock risk assessment, the answer from the national standard and the dynamic wouldn't, and the dynamic method that we presented wouldn't change. But what I'm highlighting a little bit is basically those critical conditions condition is where the absorption is basically of the outer layer is across 50%, which is the double and triple glazing, the double 6332 and the triple glazing unit 5622, where we see that basically within Paris, so comparing like for like with the national standard, we see that in our dynamic methodology, we don't have thermal shock, and as in the basically French standard for both kind of boundary condition. While what happens in Torino for a different climate is that basically we would have thermal shock with the national French standard with a boundary condition that is the same that we would use in France but extended to Torino, while we would pass instead if we use the dynamic methodology but with clear sky, but instead if we use a non-clear sky, that would cause a fail condition. So at the end, what we see is that the two methodologies have comparable results, of course, for non-critical cases, but when it comes to the most critical cases, in terms of when we use national standard boundary condition, the stresses are always lower than the admissible gun stress for both double and triple glazing units. While instead, when we use the real sky, well, the TMY boundary condition, that would result basically in a fail, and that's with real sky more than what would happen instead with a simple clear sky. And that's because mainly in a real sky I have the effect of the albedo of the clouds that are increasing the peak of solar radiation, and that in terms of delta T would cause an effect that is increasing thermal shock risk assessment. With the dynamic methodology, we are able to quantify with a better accuracy the stresses, and these stresses are normally lower the thermal stresses compared to what the national standard methods is predicting. So that's so in a way with these methods we are able to predict with more accurately what is the delta T, but on the other side we are using boundary conditions that potentially are more stressing in terms of thermal shock risk assessment. But the combination of the two makes us to use a methodology that is more precise, so we are able to quantify with a more precise way the utilization factor, and that we can use it to engineer the glass better, rather than not knowing what is really happening in terms of boundary condition and in terms of delta T. So from a general point of view, these dynamic methods prove to be more accurate compared to the NF standard due to the thermal model, but also the representativeness of boundary condition, and this results in less ground strength utilization factor due to temperature stress, meaning that the glass don't need to be over-engineered in critical situation. We could extend the national standard methodology outside of French territory because we found a way to use the TMY representation to replicate those boundary conditions outside France, so we can simply extend that methodology. This, though, marginally overestimates the temperature-induced stresses by a few MPAs. And then what we see that in TMY with real sky, we have an higher temperature stress. Finally, in this table, what we try to do is to evaluate what is the error that you saw before in the utilization factor, which is simply the maximum error that we do on the delta T divided by the maximum strength of the glass that we can assume, as a comparison between our dynamic the methodology and the national French standard, and divided between double and triple glazing unit. And what we can see is that compared to more accurate calculation, the national the French NF standard basically could make errors that are much higher than 10% in terms of then utilization factor. Going to triple glazing units, the error could become very high. That in critical condition, I think it's very important. With our methodology, due to a more accurate thermal model, we can reduce this error to less than 10%. So the advantage of this dynamic methodology is that it is we have an accuracy that can be practically used in engineering scenarios, and also having boundary conditions that have a better climatic realism, so that we can reduce eventually the use of heat strengthened glass in critical condition where we could. So we can better engineer the glass from a point of view of thermal shock. Future work will include not just standard condition, but special condition like heat pockets or shadow boxes. We want to improve a little bit how we model outdoor heat transfer coefficient, also with the exchange with the sky. And incorporate also in this methodology smart glazing and also climate change impact. So the advantage of the TMY is that you can downscale to predicted future climate scenario. So it's very easy to consider this in thermal shock analysis. What we want to do is also benchmarking with other tools and data where data exists related to temperature difference in glazing, and then that we want to pass from a semi-probabilistic approach like this to a fully probabilistic approach, but this is a kind of a big question mark. The practicality of using this tool is demonstrated by the fact that this is in an online tool, and you can use this, you can do this analysis live. And this is powered by a software house was partner of this research project. So you could try this dynamic method, and it's actually very important to try it so that we can benchmark it and we can discuss about the validity and usefulness of it. So try it, and we're happy to hear feedback from you. Thank you.